get together and provide some updates regarding the research that they've been doing recently. A careful viewer will have observed last time that Carlos didn't present at all because, well, basically we ran out of time and we wanted to discuss the hypermatrix event that we're holding next week. So we promised Carlos a nice fat slot for this week. So Carlos, without further ado, please take as much time as you'd like, and we're eager to hear some updates from you.
Sure, thank you. Let me just double check that everything is streaming properly. Yeah, all good. So, yes, I wanted to, so let me actually share my Blackboard. Um, so I'm happy to be able to say that this week we can show some, I would say, qualitative progress in the development of the functions that we set out to develop. So that's always good. It feels good when you're able to show some discrete step in progress. But before we see that, let me preface with some reminder of where we're going with this
Great.
functionality and yeah. So let me remove all this stuff because it's extremely annoying. Why does it do this? It's just okay. So the short version of the story is what's on the screen, right? So we have to go from hypergraphs to diagrams, and diagrams here means something very general, which is a string of characters is a diagram. Commutative diagram in category theory is a diagram, obviously. All kinds of type languages and code are diagrams in this sense. So we have been working on hypergraph rewriting as it was argued a few weeks ago that we're going to take this view that hypergraphs give us this parsimonious representation of many formal systems, and so hypergraphs employed for formal system representation is what I describe as a diagram, essentially. So diagrams are this very general support for formal information that can be mathematically pinned down to something, as you can see from the screen, that we call a labeled hypergraph. So I wanted to give a quick rundown of these ideas so that everyone has their clear minds about what labeled hypergraphs are in a more technical sense. And hopefully, I'll try to be brief because brief as in, I like to condense everything so I say everything I want to say, because Nick we have the functions that are doing what they're supposed to be doing, and at least as far as we've checked, we've come far enough that these functions are almost ready to be implemented into sort of mathematical utility, which to me is great progress, right? We might even be able to, I think we are able to live code category theory on the screen, so that'll be fun. So anyway, but before that, let me just say, remember that we are taking hypergraphs. So a hypergraph. Let me use the desk. So a hypergraph H essentially consists of a pair of things. So technically, you do have a set of vertices, that normally you like to consider as some kind of background, some kind of support where your data is going to live. And then you have so I think it's important to say that that's a set. And this I'm going to highlight in a different color. So this is a set. And then what you have is here a multiset of collections of vertices. And by collection here, it means something a little bit general that we described at some point. For people who are familiar with the theory of combinatorial species, it's a combination of elements. So it's either a bag or a tuple or a cycle or some combination thereof. And so you have, so I'm going to express these as generically by brackets, like if they were tuples, for example, because tuples in some sense are the most restrictive set of structures. So you could have something like one tuple or something like three tuple, and you might have repeated stuff, and so on. So importantly, this is a multiset. And the difference again is that you want the same basic mathematical structure, but you want to keep track of multiplicities, and so you want cardinalities to be accounted for with the basic behavior of a set, right? And the reason why we want to separate set and multiset at this level is that the set on vertices represents the fact that these are separate loci of data, right? These are really distinct locations where you can place your data, and multiset means that this is mostly, it's almost like the vertices are some kind of logic variables, and the multiset and the edges are the statements that you make out of these variables, right? So you can make many statements about the same set of variables, right? So that's why you want to, and they are different, and so that's where you want to account for a multiset, right? So this is the structure of a hypergraph in general. Sorry. And so we've discussed hypergraphs a great deal so far. We've discussed their correlation with hypermatrices, and next week we're going to be talking about hypermatrices all the time. We've described how if you want to develop something that looks like a complexity measure for these things, you need to take seriously the fact that usual complexity measures are based either on the matrix representation and therefore matrix algebra, or they take some interpretation of path complexity or some kind of diffusion phenomena on your graphs, and then to generalize this to hypergraphs you need to take some extra steps. So in all that investigation, hypergraphs have been essentially these kinds of objects, right? Sets of vertices and then multisets of edges that correspond, when you choose some particular sequentialization of your vertices, those correspond to hypermatrices in a very obvious way, right? Mm-hmm. So how do these sort of primitive mathematical objects become the diagrams that the formal systems are going to use? Well, mm-hmm. They do so by what we call a labeling, and this is it's a very rudimentary thing, but I want to flesh it out because sometimes it's easy to keep track of these ideas if they are very explicit. So a labeling, a labeling is basically, so it's a multi-map from edges to a collection from edges to a collection of labels. I mean, redundantly, I guess. So if you have L, I guess let's have LV and LE for vertices and edges. Although technically we really only use LE because we can always think that vertices are unary edges, but for the sake of it. So LV is essentially a set, and all you have is a map from LV to well, in this case, vertex H from LE to edge H, right? So actually, I wanted to show it the other way around. So these are maps from these to LV and LE. And again, I could just write L. It's a big enough set. It doesn't really matter here. So I'm just gonna say that I have maps to L, and the idea, and you can forget about vertices and just look at edges. The point is that you have this extra structure that is somehow typing your edges. And I mean, this is a very sort of succinct and generic way of describing labeling. Now, of course, when we look at hypergraphs, I mean, this is kind of the cartoon version of hypergraphs, which is unordered, simple, and all the desirable properties. But when you look at hypergraphs in full, what you have to track is essentially two things. You have, on the one hand, you have the basic structure of a hypergraph, which some people call a set hypergraph, which is basically a set with association structure, right? So you have a set with subsets chosen inside. But beyond that, or maybe a multiset if you want to be precise, but beyond that, you want to express what type of symmetry your edges have. So each edge actually carries a symmetry type, so to speak, and then you want to label the different elements. As I said, you can just label edges, and that reduces to that. So effectively, each edge. So if I, for example, draw some kind of ternary edge, and let me call this x, y, and z. The ternary edge here maybe can be represented as a back x, y, z, right? And a back here means that it's a tuple. It's like a tuple but with all the symmetries, right? So I could express it like x, y, z with those brackets, or I could say something like x, y, z in a circle or something. I mean, syntax is or you could say this is the equivalent class of all the three tuples that are circulated. So in some sense, this edge carries the information of the XYZ multiset or bag, but then it also carries the information that these are sitting in a structure in a specific position, or it could be that it's XYZ in a tuple, right? In which case, YXZ is different, and so on. So that's the information that an edge carries, and typically, and then when you add the typing or the labeling, all you're doing is you're saying that that this object is getting mapped to some E, which is an element of L, right? That's effectively what's happening here. So for understanding, when you look at an edge, what you have is a more typical data structure. You have a pair of a more typical data structure, like XYZ, and some kind of symmetry, and that you normally want to represent as a group, right? You normally want to say this has a group. So in this case, for the tuple, you really don't want any symmetry, right? Because you have the most rigid structure. So this, I mean, some people call it a 1 or a 0 or whatever. Let me just write 1 here. If you have something like a cycle, I mean, some people write like this. For this, you effectively want Z3, right? I mean, it's a cycle, so it's the group that characterizes the cycle. Now, if you have a bag, obviously, if you want a group that acts on representations of the bag that are set theoretically, standard, then you want an S3 action. Right? So these informations are so the reason why you're keeping track of groups explicitly in this presentation is that you want to use. So if you want to base your theory on set theory in the standard presentation of tuples and Cartesian products and so on, you have to. You can only talk about collections of objects as tuples, basically, right? There's no other structure that allows you to do that. And then what you can say is say, well, this is the group that acts on this set, right? Now, more generally, what you have is not really a group, but because this assumes that your entire set, your edge is made of a tuple, right? So it's something amenable to a permutation, right? So it's some kind of, or if you want to think in terms of sets and bijections of sets, that's also a possibility, right? But it's equivalent, right? All these things are equivalent ways of formulating the same thing. Really, what you want in general, so in a very general case, what you want is something that looks like an edge. Let me call it E, and some group G that acts on E, right? So E is going to have it's going to be a set effectively, which intuitively you can imagine this is the possible permutations of your of your elements within the symmetry positions, and G is something that is acting on that. So what's interesting about this is that really the symmetry information is contained in the group, but the edge is a group action, right? So and this is obvious, right? To when you think about it, the XYZ tuple has group action the identity. I mean, there's always an identity action on any set, right? So it's the unique group action that you have there. The cycle edge, the XYZ cycle, that can be seen as a set 3 acting on tuples, right? Because it means that XYZ is the same as YZX as ZXY, right? So those 3 tuples are the orbit of the set. So basically so E here would be that class of the set of all the expressions of your data structure that are symmetry equivalent, right? So the reason why I'm saying this is that because we are going after rewriting eventually, when we want to match patterns, this symmetry is important. I mean, you can't. It's very important to match symmetry beforehand. You're doing rewriting. Otherwise, you're going to end up in the kind of troubles that we found ourselves in the last couple of weeks, where you have partial matching here. You have if a tuple is very rigid, then it matches on like however many places when something is a bag because it has many symmetries. So the reason why I'm explaining this quite explicitly here is that you have to account for symmetry as part of the edge data. And just to add to the presentation is that this is typically not considered in standard hypergraph theory. So standard hypergraph theory is normally a direct extension of either combinatorics based on sets or network theory or more traditional graph theory. So in those cases, they either think of directed edges or undirected edges, and directed means that they have many to many. So many to many is, it's fine, but it's by no means the most general possibility, right? So we think that we have in our hands the framework that allows for a completely general treatment of symmetry, and with the computational ability of doing rewrites and using kind of a rewrite approach to make these things infuse life into this kind of system, right? Okay, so where does this take us? So we basically now have a labeled hypergraph where our edges have a particular tag that is basically a map to a set, and therefore the labeling now gets enabled. So there's a question from Richard. Let me see. This presumes no multi-edges. I assume so, otherwise yeah. So this is a good question. This is a very good question. So you could either think in terms of multi-maps. At the very beginning I said this is actually a multi-map in some sense, but but it's a very good question because for hypergraphs as diagrams, you normally want simple hypergraphs. You want to really restrict yourself to simple hypergraphs from the get-go at the set level, so to speak, and then you go into you gain the ability to represent multi hypergraphs or multi edges by simply having different labels, right? So in a technical sense, the example here being if you have 2 vertices x and y, and you have an edge, you call it A, right? Technically, if I had this, there's nothing wrong if I'm using multisets, right? If I'm basing my formalism in multisets like we are, or at least technically we are, there's nothing wrong with this. This is A is an edge with multiplicity 2, or there are 2 A edges, right? In this case, but you normally want to avoid this and actually, don't distinguish. Only distinguish if these 2 things have actually distinct labels, right? So you're likely to want to be sort of set-like for labeled hypergraphs, right? So if you remove labels, they become multi-hypergraphs. But if you account the labeling, then they are simple in this sense. They are set-like. And when I say simple, it really means sort of set-like, that distinct elements are labeled sort of traceably distinct in this sense, right? So yeah, this takes us to the rewriting part of things. So if you want to rewrite a pattern that includes labels, then the only thing you really need to update from your previous perspective on hypergraph rewriting is the fact that labels are essential to the data structure, right? So labels, I'm going to use the example of categories, and maybe we can live code it when Nick shows the new functionality. So we've used this example 100 times now, but I want to, so many times I just draw quickly and say, maybe let's do directed to be completely accurate, right? So you have this, and and then you rewrite to this. So when you see this diagram, you immediately think, categories, and this is composition of morphisms or composition of relations or matrix multiplication in graphs. You know, this is immediately what you think of, but that's not technically true, because if this is a diagram of just a hypergraph diagram, right? So sorry, if this is just a hypergraph rewrite rule, so these are just rules of writing hypergraphs, and there's no specification on labeling, then these are variable. Rewrite rules are meant to match in this placeholder sense, right? So these are variable vertices. So in a technical sense, you know, something that would look like this on a state hypergraph to be updated by this rule, something that looks like this could be rewritten to something maybe that looks like this, right? And this is, from a hypergraph theory perspective, there's nothing wrong with this. Like, that's fine. That's a rule applying to a case where it should apply. However, you really don't want this if you want to keep track of diagrams, right? Because you end up with problematic labelings in if you want these things to be diagrams. So the interesting, or the addition that you have to consider is you have to put labels everywhere, basically, right? So you have to say this is X, this is Y, this is Z, and so the labels here are important because they are basically saying, so for people who are familiar with the double push-out formalism and this sort of span diagram of in the category of graphs or hypergraphs, the context, so normally you have, you know, a context, an input and an output, right? So these are graph morphisms. The context K is the fact that you have a consistent labeling between the two hypergraphs. That's basically the context, right? And so it's essentially, in this diagram, it's essentially the fact that XYZ as a hypergraph with no edges, basically, this XYZ can be embedded in both the input and output, right? That's what the K, the context, is, in case you want to make the connection between the push out sort of formalism and the more strictly rewrite formalism. But further, you also have, in category theory, you also have labels on the edges. And so if you think about it, I just wrote some random labels on the. Oh, I just realized that I was covering the screen for the stream. Yeah, should be fine now. So you might realize that if you have labels on your morphisms, that's just a way of, as I said, it's a way to be set-like with hypergraphs that might be multi, right? It might have multiplicity greater than one on a single set of on a single data structure made of vertices. And the interesting idea that we kind of get mathematical operations for free, algebra for free in a way, is that if you're careful to label your edges on your input, why shouldn't you do the same thing on the output, right? So in this output, if I call this H, right, in principle, you say, all right, so you call that H, what is that? That's just a symbol. It's just you append a symbol to a new edge. That doesn't do much, right? Because you're assuming that everything is labeled. So what are you doing really? So what you're doing is you're actually creating some kind of causal dependence of labels, right? You're saying that the label H here causally depends on F and G. And it's customary to write something like H equals, well, depends on your convention, right? GF or FG, depending on which way to go. I actually prefer FG personally. So it's customary to write this operation or this symbol. But what this really is saying is that H has a dependence on the FG tuple, right? Because you normally, I mean, the information is the actual rewrite rule, right? It's or actually more specifically in category theory, if you find yourself in this situation where it's A, B, C, let's go A, B, C, and then you compose and you call this F, this G, and this H, and then you can state that H equals FG, right? In this case, you are somehow, I mean, all you're saying is I have a map from this sort of edges to this other kind of edge, right? In the rewrite context, there are no maps, right? Because rewrites are not maps. They're only they only produce new. I mean, they are maps between, or I guess maps between collections of hypergraphs, but they are not proper hypergraph morphisms. Nothing is being mapped between the edges. But when you relate H to the labels, what you're effectively doing is you're saying F and G as a tuple have enough information to specify H. And the trick here, and the reason why I wanted to have this exposition as some kind of reality check before we move on to more functionality stuff, is that in this notation here, that is so familiar to everyone, in the context of category theory, there is a lot of hidden information that we don't specify. Like if you flesh this out, this information is really this diagram, right? Or if you want to be very fancy, you have to say, well, H has domain X and codomain Z, and this is the same thing as doing F, which has domain X, codomain Y, composition happening on X, Y, Z, which is also labeled, and G
yes.
labeled
Yes.
on Y, Z, right?
Mm-hmm.
So this is a more faithful expression of morphism composition, right? It's how it should be written in more general terms, but obviously nobody writes that. I mean that's kind of stupid. Why would you keep track of all those symbols? But also what nobody does is to just write H equals FG and run from there, like when you do just pure algebra, when everything is in a set and everything and operations are closed, because composition is a partial operation from the traditional point of view of algebra. So what people have resorted to is doing a hybrid, right? Like you're using algebra to write things like your morphism F dagger and then composed, and you do whatever, and there's daggers inside and you do whatever. So you do some brackets and more traditional algebra notation, but at the same time you're like no, but look at the diagram. This is such that this diagram commutes, or for every object that there exists such a diagram, this will commute, and so on. So there's some kind of hybrid between the two. And so I think one of the advantages of our approach, and the reason why I was trying to remind everyone of this, is that now that we can do labeled hypergraph rewriting, which I hope that I've convinced you that this is really recovering the usual compositional structure of categories and therefore many other structures, we are able to be more firmly on one side of the computational framework. So we are not jumping back and forth, sort of script-like notation, and then more diagram notation, and then some more script, and then some plain English, and then some we are with this rewrite approach, we are just rewriting, and you can approach everything as what are the outcomes of the rewriting? Is it confluent? Does it is it reductive? Is it additive? All these kinds of questions that you can ask about a rewrite system, you just ask to the system that you're axiomatizing or that you're capturing with your rewrite rules. And yeah, that's kind of the gist of labeled rewriting and why we want it. And hopefully now Nick can show you that I think almost got it. I think we are almost ready to be able to do rewriting like properly, symbolic rewriting in this sense. So any questions about this before we move on to more functionality?
Have you tried labeling with patterns?
What do you mean labeling with patterns?
Like, it could be even more general, right? If instead of Y, you had like a pattern that matches everything, then I'm talking in Mathematica implementation, like it would match this triangle, but it would also match your loop that you drew earlier. So you could have really precise control of.
Yeah,
that's exactly what we have, kind of.
Yeah.
So I can show you how you can use patterns in labels.
Yeah. I mean, I think Nick should unless you have some questions about the mathematics of it, we can move to Nick's part.
I personally don't have any questions. I thought that was thorough.
Sure. So,
Richard?
No, it's just a comment that what Łukasz was suggesting sounds a bit like the Wolfram model rules, where a vertex can be bound sort of multiple times within one pattern.
Yeah, but then, I mean, you have like very strong control if you choose that it only matches. You can choose any pattern, right, or variable.
Mm-hmm.
I can just show you what we
ahead.
have as an idea for those pattern labels or whatever, and how it is different from the Wolfram model, and their very strict or lack of control of those labels patterns. Okay. All right. So this is the example that Carlos just showed. I just retyped it, but I guess I should start with something much simpler. Try to understand what's going on. Okay, so forget about this for now. I'm just gonna show you what we have. For example, taking this simple hypergraph, which is gonna be in the end somehow our left-hand side of our rule that we're gonna use, right? What does it mean to just strip it of every options, right? Just nothing else. It's unlabeled hypergraph. It's going to be used as a left-hand side. And when there's no labels, it basically means we have like a special function for that, to labeled pattern edges. If you turn it into a pattern, it's going to be a very complicated mess, but we kind of can, I know, unwind it a little bit. So it turns every edge in this orderless pattern sequence, first of all. That basically means because we have a symmetry assigned to each edge, right? And because by default it's unordered, that means if you use it as a pattern, you can like permute every vertex however you want. It's like another way of doing it is this edge symmetry option that we have. This allows us to control every symmetry of every edge individually. Like we can assign to this first edge like a simple symmetry, or maybe like nothing, right? Then it just turns into our identity. This is like instead of orderless, this become alternative, but this is the same thing. But the first edge kind of stayed as it is, verbatim, right? There's no orderless pattern sequence. There's no alternative that you can swap vertices around. So because there's no symmetry and it is a simple directed edge, okay? Right? And the second one is still unordered, so we can have either X, Y, Z, either Y, Z or Z, Y. You can switch vertices around.
Wait,
but it also has like
Nick,
some...
One quick question.
Yep.
Why does this X sub dot appear? Is that... What is that?
It's just a name.
Okay.
It's just prefix for all the pattern... So for all the vertex pattern labels or whatever.
Okay, sure.
No, so whatever name over the vertex is, it's getting prepended with this X dot.
Okay.
Just for safety, maybe.
Sure.
There's no symbol like that.
Yeah. I understand.
Okay. And you can also notice now the labels, okay? Because there's no labels now, this is completely unlabeled hypergraph or left-hand side of our rule. If you make some label or make them all automatic, which is assign a unique label to each vertex. Right now, you can see that this each vertex now is labeled. Now I presented bit L, okay, so that it represents a label. But it also adds this additional constraint to the whole pattern that all the labels are different or unsame, right? So not which is just a symbol in the Wolfram language. So the different labels now. So whenever we have automatic vertex labels like that, it means it no longer can match the an edge like this, for example. If it's a binary edge, it can no longer match edge like this. It's a binary edge, but it goes from the same vertex back to itself, right? So as soon as you restrict itself that the labels are different, and by default the labels for this thing is just the same as the vertex itself, it can no longer match it. Okay, so that's how you kind of can control the this matching capability. So you can assign any label to a vertex. For example, to vertex X here, you can say it blank. Oh, hold on. Not everything, but everything else is automatic. I guess you should do it like this. Okay. Now the vertex X is anything, but the constraint only considers Y and Z. So that's where you basically control your labeling with any patterns. You can depending on what labels you have, you can use any Wolfram language pattern right here, not just blank, but alternatives, optionals, whatever. So that's how you control it. I guess you should see this bigger example that we had here. Maybe so. If we're gonna try to write, let me put this rule.
Yeah, maybe
Now
just for the sake of illustration, try to remove the arrows, right, from the
arrows here.
Yeah.
Yep. But there are no others.
Yeah.
So what we're trying to do is to apply this rule to this hypergraph, right?
Okay.
Hold on. Let me remove the
Yeah.
arrows from here. And as you can see, you can apply it only 3 times in 3 different places, right? So that's what you kind of get, and you can. But if you remove the labels or make the hypergraph that is the left-hand side ordered instead of 3 matches, I think you just don't get anything because the symmetry doesn't match.
The symmetry doesn't match. That's why it doesn't match. Yeah.
That's kind of But if you can do it, make it match if the target hypergraph has the same symmetry, maybe. Or hold on, what happened?
Because it's ordered.
Okay, up to some bugs, or maybe.
No. I think.
Or because it's.
No. I don't think that's a bug. I think that you might have no matches depending on how you drew it, basically. So you have to.
Oh yeah, I see. Because I have X, Y, and Y, Z, but I always have from A. Yeah. If I switch this around, this should match.
Exactly.
3 times. Yeah. But when we had another symmetry, you kind of allowed to swap them around anyway without specifying it explicitly, because you kind of when you specify that this edge is unordered, you consider it's either XY or YX by default because you're just assigning it as another symmetry. But now it's ordered, and it matches as like this. Okay.
And something interesting to point out here is that the idea that we are pattern matching the symmetry type of the edges allows us to have pretty good control of when rules apply, and because in the unordered case you really want to, if you see a match for your unordered hypergraph, there's just that match because everything is in order. There's no sense of there's permutations of those things, right? I mean, if there's some kind of permutation, it's going to be a different embedding of the same pattern in the hypergraph. But with directed stuff or more structured edges, you're going to have multi matches, right? And so maybe one illustration could be, Nick, if you define the rule for morphism composition, so labeled, right? ABC, like what I was doing in the Blackboard a second ago. So basically the same rule you have above, but with directed and A and B. So it's that rule. So
Well, this is the rule.
yeah, that rule.
Right.
So X, Y, Y, Z, but then yeah, that's the rule. Yeah. But make it ordered.
Well, we don't have different visualizations for those, but
Sure. But I mean, maybe I mean
Okay.
show the arrows and then one example that we could do. I mean, this is just kind of to close the loop here with my presentation. Is I mean now
Mhm.
you have effectively. Oh yeah, because the target needs the arrows as well.
yeah.
Right. Oh, it affects hypergraph rule as a whole as well. Interesting.
Yeah, it affects both left-hand side and right-hand side.
Okay, interesting.
If you do it for the rule.
Yeah. So the idea is now you have this rule, like you can call it whatever, like maybe you give it a name like comp or something like composition, and then
I just call it the rule.
yeah, rule whatever, and then you draw. Now you draw. So call the. So this is going to be the. Or maybe I could do it, but you have the notebook there. So maybe call the hypergraph draw for people to see what you can do now. It's like you call the hypergraph draw, and you're like, okay, let's do some commutative diagrams. So draw some commutative diagram, right? Although I guess, yeah, it doesn't matter.
No,
It's going to be
depends on
labeled
what
by default, so it's fine. Yeah. So, oh yeah, these are undirected by default, but yeah, they're gonna have some. Yeah, I mean, draw a few so people can. Well, yeah, I mean, that's not gonna compose, but
Well, what kind of
just draw like 4 or
What kind
5
of diagram
vertices
do I-
and like some arrows between them.
like anything?
Yeah.
What?
Like some paths, so there's something that composes. Yeah, that's gonna compose.
Like what can this do?
Yeah, sure.
Yeah.
That looks good. So now we have the state. Yeah,
Mhm.
and so that's a diagram that you can draw. You know, in your learning category theory, it's like, okay, what morphisms can I get, and so on. And so now you just apply a rule to that. And ooh, what?
Well, let's see. Because this one
Because that's probably unordered by default.
it is, but why? For example, this
Be-
should match, right?
No,
Two,
but
three,
no, but
two,
the
four.
symmetry,
Oh,
is
you have
failing.
two arrows.
Yeah.
Yeah,
So
yeah.
Just define it
But
as
what about this one?
No, but the symmetry is failing. Like it's checking for symmetry. It's doing.
Oh yeah.
Yeah. Just wrap it with hypergraph and ordered.
I kind of still haven't accepted that.
Yeah.
We should-
you did the implementation.
We should
You don't even believe it yourself.
we should match the symmetry.
Yeah.
Kind of force it.
Yeah.
Kind of weird.
Yeah. Now you get the different. So for example, that first hit, everyone can see
Mhm.
that it's composing the path that goes 4, 5, 1. Yeah, you can see all the paths, right? So this is it's doing composition, right? It's like you're rewriting your diagram with morphism composition, and what I want to highlight here is that I mean this is an overkill. If you just want to do category theory, this is obviously overkill, but the crucial point here is that we just made an example, and there's like this is as difficult to do or as sophisticated as any other thing that we can come up with, right? So we are now squarely on this Rulia land where we can explore all these xeno-algebraic things that are living around us. So it's quite exciting to have this functionality almost ready.
Yeah. There's also some new kind of small features I can show.
Oh yeah.
really quickly. You can use tagged edges now.
Oh, yeah,
This is
that's
the
true.
new tag. This is the new edge, right? And you can tag it, and you can. It's kind of
Okay.
nice. Going to be nicely shown because I have
Yeah, that'll be
labeled
helpful. Yeah.
edge tag labels, and you can use it with the pattern matching too. For example, if I force it, okay, I want this tag to be exactly tagged. Now it's not going to match unless
Yeah.
some edge is going to have the same tag here. Okay.
Uh-huh.
Now there's only two of them because I can no longer match
Ah.
against these two. Okay.
Why
So
doesn't
you
it
can
show?
control.
Oh, because it's only showing the rewritten one. Yeah, I see.
Yeah. You only can match against this edge with this one and this edge with this one.
Yeah.
Okay. One of them is kind of restricted to be with a particular tag. And you can use pattern here if you want.
Yeah.
Like if there's like some complicated hypergraph. This is have tag 1, this is some string, this is 2, and here you can say, okay, I want some integer. I think it should maybe work, maybe not.
It matched.
Then, anyway, oh well, maybe it's not that good, but forcing it, whatever.
Yeah, but it's but you can certainly you can certainly match labels, right? So these are edge labels now. So you can so this is perhaps completing the category theory simulation here is that you now have you could label all your morphisms in the previous diagram, and then they are going to get matched because you could, for example, in the rule above, right, when in the rule that we have defined above, Nick,
Yeah.
couldn't you just specify xy goes to f, yz goes to g, and then xz goes to fg, right? I guess you need to. I mean, couldn't you do that with patterns?
In a way, yeah.
Sure. Yeah, because that's the point, right? Yeah. But you could, in principle, make f and g a pattern, right?
Yeah.
And then, but then how do you specify that whatever was the pattern fg comes out?
So let's try it with whether it works or not.
Yeah, just run it like
Well,
that, right? For now, see if it works.
okay, yeah, but it's not gonna work. You want so that I can use these patterns, pattern bindings here. That would be cool. It's like, but it's not supported. It's like you could do something like this because it's a rule and this is the right hand side, and somehow bindings propagate from this to here. Yeah, that's a cool feature. I'll think about it. Yeah, it would be nice to have.
Yeah,
Like,
but
so
now,
that- so that-
so if you run it now, just run it, see what happens.
That's gonna always be f and g,
Sure.
even though this actually matched somehow inside against
No,
one.
that's what I want to
this
see.
S.
It does match. Yeah, that's what I want to see. Okay, sure.
Yeah.
Yeah, we can think about that because
But,
it's
yeah.
interesting.
If this binding would propagate, I would like to see, like, instead of this f composed g, depending on what edge it matched, like one composed s composed 2, you know?
Yeah, that's the holy
Something
grail.
like that.
Yeah, that's the end of the program. In some sense, that's kind of like getting to the end of having formal systems as diagrams, as labeled hypergraphs. Now, obviously, we still have to flesh out like other parts, like complexity and spectral theory and so on, and hypermatrix part. But yeah, but this is a glimpse at the end of what we proposed a few weeks ago. It's kind of cool.
Mhm.
All right. Anyway, I took way too long. Or we took way too long.
I suspected that between Carlos and Nick, your joint presentation would consume basically all the time. That's okay. Well, Mhm. It's 3 minutes until the hour. Um, I mean, I've spoken with Richard and Wukash recently. I know Wukash is operating on um, some some prime number of hours of sleep, less than 7. It's not good. And I know Richard has like a few small things prepared. So I'll leave it up to you two, Wukash, Richard. If you want to present something now, um, we'll gladly listen. If you want to wait until next time, then we can have you go first, and then Richard and Nick can go after you two. It's up to you.
I'll let you go first, Wukash, and to be honest, I would prefer to wait until next time. Um, but I can speak briefly. But yeah,
Yeah,
Wukash.
I can wait also. Also can speak briefly. I think I haven't finished this Harishchandra, but I think we got pretty close.
Yeah, I'll say one thing about Langlands is I think we actually completed this theoretical review this week, and so now we can actually kind of type up this review that's been like 6 months in the making. So um, there's no specific functionality to show from that, but there are some things that Wukash has been making that'll be available next week, and 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 also there's a nice kind of computationally informed review of um, the L group and automorphic L functions and everything, which I think we finally have ready. I know Richard has some very interesting things to show as well, but yeah, I
Yeah,
personally don't mind. I don't mind if we wait um, until next week. I'm not exactly sure how we'll organize it next week. It's something for us to discuss because we'll be in hyper matrix mode. We'll be red pilling all week. So we'll have to find some. I gotta be careful. Maybe I'm not sure if there are kids who actually watch this.
But that could sound very bad. Correctly.
They're vitamins, Anyway,
yeah.
yeah. Um,
Nootropics. It helps your brain. But yeah, I mean, I can just speak very briefly. I've been trying to develop functionality to sort of identify distinct states within a program and then convert that to the graph representation. And then there's still a sort of complication around how to sort of rewrite them whilst preserving their behavior and how to actually show that's being done. And then I've collected some nice examples. We were discussing, James, on the phone about how, I mean, since this language is basically doing unary operations, certain mathematical identities.
frac trend.
Yeah, yeah. So
Yeah.
certain mathematical identities are sort of as efficient as each other. So, n times n minus 1 over 2 is the same as just the sum from 1 to n. And you're not getting any efficiency because multiplication is kind of more expensive than addition in this world, which kind of, so it's not like your ALU on a physical chip where, they have the same cost or something. It's like,
Mhm.
this unary operation is your fundamental unit of energy or something, and that's. But anyway, and I've collected some examples, but where I mean, actually, I just very one less than a minute just show the example I have here. This example that you see on screen is actually the two prime generating programs. And you see somebody found a sort of shorter version.
Mhm.
And so what we'd like to have is that you sort of bump into this one first before you find this one, and therefore, this is kind of, and who knows, maybe there are shorter ones, and that's the sort of open question for a complicated program like that. How small can you make it, and is it possible to sort of prove that you have found the minimal form? So yeah, and anyway, identifying distinct states of a program is also kind of tricky. So when you're writing them by hand, yeah, you can sort of label them yourself, but if you're just given a program and then having to extract states from it, that's kind of hard. So I have to really think about that. But I did have a question for Nick and Carlos before we close, a brief one. Yeah, which was are you just going? Are you just focusing on sort of single way rewriting, or is the functionality you're developing going to give you sort of multiple? So if we have like a set of rules, are we going to have? Or is that going to return a set of like non-overlapping rewrites, or for now are we just focusing on single way?
The
Sorry to jump.
functionality, I think,
It's
it,
not really a
it,
single way
Hmm.
because you have a overlapping. You can have overlapping matches. You have a rule, and even a single rule can have overlapping matches, and it
Right.
outputs all possible outputs, right?
Yeah, but
I think
for example,
I think the
in the physics
functionality
project, in the physics project, we try to sort of apply as many as we can that are non-overlapping, right? And then we list all possible, the set of all possible non-overlapping rewrites given the rule set.
Yeah, well, that can be extracted because it is a as you can as you've seen when I apply the rule to the hypergraph, it
Mhm.
outputs the whole association with a bunch of information, and you can easily
Right.
extract some information what actual edges being matched, and you can then
Right.
check okay whether those edges are intersect. If they
I see.
intersect, then they
Then
overlap. If they don't,
throw
they
them
are
away.
kind of
Gotcha.
space-like
Gotcha.
separated.
Yeah. Cool. All right.
Yeah.
Yeah. I
That,
just was,
as a complement to that answer, yes, the functionality is being quite general in that sense. But for example, when we want to make the connection in something that I discussed last week, the connection, the correspondence between rewriting and matrix algebra. Right. This is one of the powerful concepts that we want to implement. That requires doing some extra work on the rewriting side. So we are currently implementing the functionality of a rewrite rule, not so much functions that do the things that we want eventually to do, right? So one of the examples, there are two key examples. One example is the rewrite analog of adjacency matrix multiplication, right? Which takes a graph, or maybe takes two graphs and multiplies them and gives another graph, right? It's an operation on graphs because it's an operation on adjacency matrices. So that can be expressed in terms of rewriting, but with single rewrite rules like we are applying, you have to define some algorithm, right? It's some output algorithm.
Can I ask? Are we, or have you ideas of how to extend it? You've like the graph Cartesian, tensor, lexicographic. I'm just listing the list that I found on here. Rooted product. There's so many sort of operations on pairs of graphs. I wonder how we could sort of generalize to all of those.
So I mean, all these there's two ways. I mean, there are many ways of operating graphs in a conventional sense, and I would say there are effectively two large classes in conventional graph theory. There are essentially two large classes of operations for graphs. There's one that is kind of outer, some kinds that are outer, and some others that are inner, right? And so outer operations essentially deal with the data structures of vertices, right? So if you, the data structures built on elements, which are both vertices and edges, right? So if you take, for example, if you have a construction for sets, whatever it is, tuples or Cartesian product, or you have power sets and things like that, that construction is going to apply to graphs because graphs are just pairs of sets, right? So you will be able to, and you want to make things compatible and so on, and so it has some structure. But so there's a large class of operations that are of that kind, that's kind of outer, right? Then the inner operations are the ones that are defined in terms of the specific data of graphs, right? So the conventional example of an outer operation of a graph is the Cartesian product of a graph, right? And the canonical example of an inner operation of a graph is the adjacency matrix squared operation, right?
Right.
Which gives you that. So what we want is to eventually be able to describe the inner ones. The outer ones, they are somewhat easier because they are really only dependent on how you treat the vertices and edges as data structures themselves, right? But the inner, so they, in some sense, they don't really care about the specific structure of a graph. They care about the fact that they are graphs. So they have the generic structure of a graph, but they don't care about the topology, the specific topology, right? So, but the inner ones normally do, and That's why so you want some interplay between algebra and topology and that kind of game. So that's where we are mostly after. And so there's the basic rewrite implementation, and then there will be the definition of certain algorithms that are equivalent. So on the one side they are like explicitly matrix multiplication, and the other side are some explicit algorithm that tells you apply this rewrite rule to this graph in this way, and you have some loop, some finite algorithm that tells you what is the output graph, right? So that's the sort of game that we want to play. That on the algebra side, it's been kind of exhausted. Spectral theory and all the fancy stuff, it's been kind of, maybe not exhausted technically, but there's been a lot done. But on the rewrite side, we are in much more of the initial steps of what we can do, and especially when you go to higher order, because in higher order there's just almost no results. So it's one is as good as the other, right? And the rewrite seems much more intuitive in a way, much more easy. It's easier to control. It's easier to set out and try things. Anything else? Don't see that we...
Just for some quick background, one thing that Richard is working on is trying to spatially parameterize programs themselves using Fractran. He's found that Fractran is particularly amenable to this. However, he's also found that there are these kind of equivalents. You can probably specify these equivalence classes of these different programs. And so before just creating a space of these different Fractran programs, he wants to try and remove this redundancy, so you can actually ensure that you have some space where each of the programs are kind of distinct. You don't have it be kind of distorted by these equivalent copies. Now, as I understand it, actually kind of confirming equivalence or non-equivalence between these programs.
It's undecidable, yeah.
It's undecided. Yeah. So you'd have to, if you're going to actually try and spatialize, this is something that Richard and I are finding, is like with time, we just get brutalized by these kind of issues of undecidability, etc.
We need an oracle to solve our problems, and then we're fine. That's all we need.
I wonder
the oracle from the Matrix. We should.
Yeah, I wonder what kind of agent that oracle would be in this day and age.
Now, is Oracle the sweet woman with the cookies?
Yeah. And what? And she has that thing written above her door. Yeah. Above her door, I forget what it says. Carlos will know what that is. You don't remember what it says?
Yeah, Carlos. Yeah, what was the insignia above the door?
It was a Latin motto.
Know thyself or something.
Wasn't it a Latin motto?
Yeah, it's like know thyself.
Know thyself, I think so. Yeah.
Know thyself. Anyway, but if we can find some sort of proof technique, like some way of, given a pair of programs, you can somehow sort of rewrite one to the other whilst deriving some, formal statement with the process. I mean, it's kind of verging on automated theorem proving in some way. So like given two sets of fractions, can you sort of rewrite one to the other and show that they perform the same computation? In that way, it's like semi-decidable. It's sort of like undecidable in general, but there will be cases for which it is decidable and cases for which it is not. So
and
we
you
have
never
to
know which one.
exactly. Yeah. So that's a bit of a roadblock in this thing, and it might mean that it's just okay. We can speak theoretically about it, but computationally we can't do much. And so maybe that's a sign to move on.
You can show some computational examples that are somewhat arbitrarily procured. So you can say like, you've enumerated this many programs, and up to this kind of computational limit, they don't appear to be equivalent, but it's still highly provisional.
It's the same problem I'm facing with trying to use rewrites to sort of enumerate this equivalence class. I mean, that's one way of doing it. The other way, last week I showed you a program where you just change the numerator, and that gives you some equivalence. But that's really trivial example. You want to kind of be a bit more general and start to actually manipulate the sort of graph representation of the program. And so the problem with that is it's not just rewriting, it's like rewriting under some preservation. It's like every time you do a rewrite, you want to sort of show or know that you still preserve the same behavior somehow. And so it's a bit more complicated than just match a pattern and replace it with something. It's like after you do the replacement, you then have to perform the equivalence proof or something like that. So the problem exists in a few places. This is the same problem. Yeah.
Well, I think we can hold a more in-depth discussion about this
Yeah.
next week as well as Langland's.
Cool.
We should probably wrap up for now. But
Yeah.
okay, special thanks to Carlos and
Thank
to
you.
Nick for their joint presentation. And thanks for all the viewers. And we hope to see you next time in the Hypermatrix.
Yeah.
And so, if you attend, I'm sure you'll like it. If you don't, you'll wake up next day and believe whatever it is that you want to believe. All right, guys. Well, see you then. See you next week. Cheers.
James, should we stay for a second
Bye
here?
bye. I can give you a call.
Okay.
Okay, cool.
See you, everyone.